working? Yeah?
Should we just record this session also of yours?
Mm-hmm.
Yeah, it should be fine.
Recording in progress.
Okay, should be fine. I click here.
Yeah.
All right. So here's the hands-on session of MsSpec. So we will try to make some practical example. So as Didier showed you in his talk, there are many spectroscopies that can be modeled by MsSpec. But we will only concentrate on one spectroscopy, which is the photoelectron diffraction spectroscopy. Because it is for now the only one that is interfaced with the Python language, and we decided to present this this way of making the calculation. A spectroscopy that is really close to the photoelectron diffraction is the Auger electron diffraction. It will be also available in few months because this is really close to photoelectron diffraction. But anyway, all the parameters or techniques that you will use today, this is transposable to every kind of spectroscopy. So this is the same methodology, whether you are using photoelectron diffraction, Auger electron diffraction, lead, EXAFS, etc. So it will be, you can map what you learned today to other spectroscopies. So, to begin, I don't know if it's work. Okay. So because repetition is the basis of learning, here is the setup of the experiment. But personally, I do have atomic resolution here. So here is the light input, so the X-ray. And you have the surface of your sample, which is here, and the bulk of your sample, which is here. So this is the atoms. And the X-ray is absorbed by this atom. So in photoelectron diffraction, we call it the absorber atom or the emitters. Because the absorber will emit the photoelectron. So the photoelectron will be emitted toward the detector. And especially in photoelectron diffraction, sorry, I try to move this. In photoelectron diffraction, so you excite usually a core level that creates the photoelectron. But in Auger, you can also make use of an Auger process. And this photoelectron toward the detector will encounter many scattering events. This will create other scattered waves that will interfere together to create the signal that you will measure at the detector. And in a property that is really interesting, so Didier talked about this during the last presentation, is the scattering factor, which is represented here. So the scattering factor, basically, this is how is redistributed the photoelectron intensity after the scattering event. And when you are using a photoelectron that is in the hundreds of electron volt or kilo electron volt range, this scattering factor, the shape of this scattering factor is like this. So this is strongly forward peaked. So it means that you will have a reinforcement of the intensity along dense atomic direction. So if you have a sample, a cubic sample, for example, you will typically have, if you do a polar scan, so you can make a polar scan, meaning that you will rotate the sample. So here is the normal, here is the surface. So you will rotate the sample like this, okay? So here's the polar scan. You can make azimuthal scan by rotating the sample like this. So if you make a polar scan, typically for a cubic sample, you will have a forward peak at 0 degree, and you will have also a forward peak at 45 degree, okay, due to the cubic cell. And the other peaks are due to interferences. So this kind of peaks is really easy to understand by hand. to see the structure, and you can even see if the structure is tetragonalized because this peak will be shifted around high angle or small angle. But this kind of interference is difficult to understand by hand, so you have to make some calculations. So simulation is needed for reproducing well the total signal. And this is done by MsSpec. And so by MsSpec, with MsSpec, running a calculation means write a Python script and run that script, okay? So I don't know if you are all familiar with Python, but this is really, really basic Python, so don't worry, really basic Python. So typically, depending on your installation, you will have either a front-end command, which is called MsSpec, and there is a flag option, which is -p, and if you give that option, it is like if you use Python directly, okay? But it will use Python with MsSpec, Python MsSpec aware, okay? So, but I guess the installation we have for the moment is we are in a virtual environment, so you will just have to run Python, the name of your script. Easy, okay? But you will have to write the script. The difficulty. So this script, so the very drawback of this way of doing things is that even for simple things, you need to write some few lines of code. But for complex things, you will have to write also lines of code, but it is less complicated than doing this by many calculations, then export to a plotting software, making. Oh. So it is a kind of arrangement to find. So here is a really basic example for creating a small cluster of copper and plotting the polar scan for the photoelectron diffraction signal. So the first part here, I do not calculate anything in this part. So I will just walk throughout the script, and I would suggest that you open a text editor, you write down this by hand, you understand the line, and you do this with me, okay? We have few tutorials. So this one is the very basic one. This is a step-by-step approach. We have a basic one for the copper photoelectron diffraction pattern, and then it will be more and more complex, and I will let you time to do this, and I will give you the correction in the end for you to have a script that works and that can be used for you as a template for future calculation. So in this script, so usually in a Python script, there is the shebang line, which is the first line. As in every script, you describe which executable will be used for that script. It is really not mandatory, but it is recommended to put it, okay? And the second line is the encoding, sorry, for the text file. And usually it is UTF-8. So you do have to write those lines. It's like this. Now in Python 3, this line is not mandatory anymore, but let it doesn't hurt. So here are really the lines that are interesting for us. So in a Python script, you have the import statement. So everything that is outside the core Python will be imported here. And then you have the true line of code. So for the import statement, so we need from the module, the package MsSpec, we need a calculator, which is in the module calculator, which is called MsSpec. So this is the MsSpec calculator. So this is pretty much, as I don't know if the guy of ASE showed you this on last Monday. This is the same thing as importing a calculator from ASE, for example, from GPO, the GPO calculator. You can import calculator for VASP, Abinit, etc., depending on your installation. And this will be also the same thing for SPR KKR. So this line is for importing the calculator. So you will need that line in any script for doing MsSpec calculation. The second line is to import a special function, which is hemispherical cluster function, which is located in the utils module in the MsSpec package. So why is this function needed? This function is needed to create your cluster because contrary to the SPR KKR that we saw yesterday, in MsSpec we work on a cluster of atoms. It means that we need a certain amount of atoms that are shaped in a certain form. It may be, usually it is hemispherical due to the escape path of the photoelectron. So you do not need as much atom in the bottom than in the surface. But you may need also a cylindrical cluster, for example. Especially if you are doing some calculation at high angle, grazing incidence, for example, you will need a large surface even for the first 2 or 3 planes below the surface. So this kind of function can be used to easily create a cluster. And this is not included in the ASE package. That's why it is in the MsSpec package. And then here are the lines from the ASE package to actually build your bulk structure, your cluster, the pattern that will be used to create your cluster, and to visualize it with a simple viewer of ASE. And here are the lines. So to create a bulk copper cluster, it is easy. The first line is to call the bulk function of ASE with the copper as element. ASE knows that copper is FCC, but you can specify another structure if you want. You can give it the lattice parameter if you want it to be something different than the normal lattice parameter of the copper. And finally, there is another keyword that is really important to us, is the cubic. It is a Boolean value. Yeah?
You make the character size
Bigger. Oh, sorry. I thought about this. So you have that file on your computer. So go, are you all connected to the X2Go station? Yeah. So you go to the /tmp folder, and there will be, thank you, Peter. I forgot. So I show you. So you connect to the station. Here, you know, I am in the tmp/msspec_tutorials. You can. Is there a Zoom anywhere?
I think go to view. Yeah, under view you can change the font size.
Under view. I mean, in the terminal, you mean?
Yes.
Yeah.
Zoom in.
Yeah. Peter, tell me.
Good.
So here you are in the MsSpec tutorial folder. If you do ls, you will have several folders, so you can directly copy those folders to your home folder. Copy this to your home folder because you will work with this. And in each folder, you will have the same thing that I am projecting toward the screen. So if you go to, for example, copper, so you can open the PDF for copper, and you will have this. Is that okay for everyone? Yeah? Yeah?
Is there an easy way so that I can install the Python module local, so I can locally? Just so I could work
Locally on your computer?
yeah, only like the ASE Python module.
Only the ASE Python module? Only ASE?
Yes, because I would work, then I would work on my VS Code.
Okay, so to install ASE, this is easy. So if you have Python installed,
Yeah, the ASE already here.
already here.
Yes, but I'll need the module for my MsSpec, right?
I'm sorry, you would need
I'll need the module for
the module for MsSpec? No, this is not easy to install. I'm sorry. I'm sorry. That's the trick. But I will provide a more easy way to install it. But no, currently it's not easy actually. Okay. So this is so this line, yes, the cubic keyword means that we will use the cubic cell, not the totally reduced cell of copper, meaning that there are 2 atoms per cell here. So this is not mandatory, but it is easier for us to see because here we have 3 vectors that are normal to each other, so it's better. And then to use the hemispherical cluster function, you will provide this cell, the copper, so the basic pattern, and it will produce a cluster according to that pattern. Here are the number of planes that you want in your cluster. Okay, so here I want 3 planes. And here is the emitter plane, meaning where is located the absorber atom in the cluster. Okay, so numbering starts at 0. So it means that I have a 3 planes cluster and my emitter is totally at the bottom. Please, do you have any problems? Yeah? Sorry? TMP
Maybe
cannot change directory.
This
This is this problem?
Maybe permissions are wrong. Or
Can you copy it?
Yeah, you can copy but not move it.
You can copy, but you not go then. You go down to the folder. Yeah.
where should it be? Can you write on the blackboard?
File location. Yes. No. TMP. TMP MsSpec tutorials. No, this is not the right folder. It's the previous attempt, perhaps.
Yeah,
Yeah.
if you go in the folder. then
Easier to go to your
Yes.
folder and
So this one you can copy it. You can go
It's
down.
empty. There is nothing inside.
Someone remove something from the folder. So I recall you that copy is CP, not ARM. Thank you, Alberto. Yes, oops. Totally disappeared. Okay.
yeah, somebody. I have.
Yeah, we do.
I did. I can see in the DLP file there are
Yeah, but that's not good enough.
Okay, so it's it's now there. So is everyone able to download this file now? Yeah, it's okay? Fine? Okay.
Did you using copy the dash RF to do recursively to copy everything included in the sub?
Yeah, CP minus
RF, copy dash RF.
RF. Yeah. CP dash R, and this is TMP MsSpec
Without the
tutorial. And you can put the everything star if you want, or
and dot at the end.
and this is still the okay. For example, in your folder. Okay. I thought it should be a great way to share something, but okay. So let's move.
Sorry, could you maybe repeat the cluster line because we were copying stuff while you were copying?
The cluster line,
Yes.
you will try to understand this. So this function, the first argument of this function is the pattern that you will use to reproduce, to produce your cluster. Okay, so it will be repeated along X, Y, and Z axis to create a huge things. Then it will be cut in twice part to get a surface. And then it will shape as an hemispherical shape, okay? So this is for copper. You will specify the number of planes you will be using, so 3 planes, so it will be a small cluster. The diameter will be computed according to the number of planes you are willing, okay? And you wish to put the emitter, the copper atom that will absorb the light, at the plane number 2. And numbering starts at 0. So it means that there are 3 planes and the emitter is totally at the bottom, okay? So this is the hemispherical function, and you can normally view the cluster. Are you able to do this? I will try to make it with you. So, okay, can you see this? Are you able to have this? Your copper cluster, okay? 3 planes, 1, 2, 3, and the emitter atom is the one which is at the origin, 0, 0, 0, and this is indeed in the 3rd plane, plane number 2, okay? Everyone is okay with this, right? So so basically the hemispherical function, okay, which is here, can also produce cluster that are bigger, of course, and you can specify, instead of using the number of planes, for example, you can specify the diameter that you want, and it will create a cluster with as many planes as necessary to fit that diameter, okay? And you can also specify a shape keyword with the cylindrical value to shape your cluster as a cylindrical shape, okay, cylinder. So as an example, here is the use of a more complex structure by ASE, cesium chloride, for example, bigger cluster, and here there are 2 atoms in the primitive cells. So you have to choose which one is the emitter, okay, and where to put it. So this time, to define such a structure, so you can go to the ASE website. So there are two main reference, 2 main websites to look at when you are doing MsSpec calculation. So this is ASE website, where there are a lot of tutorials and a lot of documentation. So contrary to what has been said, I'm not an expert in ASE. The secret is that I read the documentation. So go to the website and read the doc, because it's evolving. Every week there are something different. So you cannot be an expert, but you can read the documentation. And if you do that, you can look at how to create a special structure like the cesium chloride here. So you can use the crystal function in the space group module, for example. So it is more general function to create things. You specify the space group, the cell parameters that are just a list of A, B, C, alpha, beta, gamma angles. And the basis is where is located your cesium at the origin and your chloride atom. And here, the hemispherical function I used is somehow different. First, as you have 2 different atoms, so cesium and chloride, you have to differentiate them to tell which one is the emitter. Okay? So for this, ASE has a special attribute, which is the tag keyword. So in ASE, the atoms object, which is this one, is a list of atoms. Okay? So you can access the atom, the cesium, in this list by doing CSCl 0. This is the cesium. But CSCl 1 is the chloride atom. Okay, this is just a list, a Python list. And each element of this list is an atom object. And this object has an attribute which is called tag. By default, this attribute is 0. And you can change it to tag your atom. And many atoms can share the same tag. Okay? So in that case, in the primitive cell, we will set the chloride atom to be tag number 1, and cesium will be tag number 0. So in my hemispherical cluster function, to specify that my chloride atom will be at the origin of the cluster and will be the emitter, I just say that the emitter tag is 1. The emitter plane is number 3. So here, I'm not too tall. So here, 0, 1, 2, 3, okay, emitter plane. And the diameter, this time I choose the keyword diameter, so this is 25 angstrom, the unit is angstrom, okay? And the hemispherical cluster truncated the shape of the cluster just to fit the diameter, okay? So it means that the emitter is here, and you have many, many, many planes below the emitter. So this is not really useful in photoelectron diffraction, because you want to see the photoelectron here, so you're not interested in what's going on too much here. But you have to change accordingly. Perhaps a better way, if you want, is to use the plane keyword, but you will have a reduced diameter. Otherwise, you can also, after this, it is still an atoms object, so you can remove planes after. So you can reshape it after. Okay? So this is just an example of how to use the hemispherical cluster function. So if you want to have more example and documentation, some of what has been said but written, you can go to the website of MsSpec. So the website for now is not very, very full, plenty of information, but there is the essential. So here, so the address is msspec.cnrs.fr, easy. You have some menu here. So normally there is the Learn from Tutorial menu here, but it was a bit outdated, so I will put the new version of it in few weeks. This will be what you are doing now, okay? If you want to have some more information about the hemispherical function, this is in the FAQ, hemispherical cluster function. So it is written, what I said here is written here. So you can have example on how to create this. Okay? So this is the second way of finding information. Of course, in that website, every module the source is given, so you can look at modules, and some modules are also there is some documentation inside the website about the function that we use. For example, I don't know, calculator, yeah. Okay, for example, in the module calculator, to create an MsSpec calculator, it is written how to use the function. So it is actually, this is an application programming interface. So you have the documentation here. Okay. And now, how to do the calculation. So we were just here. Let me say, no, here. Okay, we were here. We put the view function to view the cluster. So that's the way I do it for checking that I'm not doing something wrong, that I have the right cluster that I want. And then when I'm happy with this, you can remove that line or comment the line with a hash sign in front of it. And then here is the rest of the procedure to make a calculation. So first, you have to tell which atom is going to absorb the light. So this is called the absorber. This is an attribute of the cluster object. So cluster.absorber is, and here you need a number. This is the number of the list, in the cluster. Cluster is an atoms object, so this is a list of atoms. So you just have to pick up the index of the atom you want to be the absorber. But as you used the hemispherical cluster function, the absorber is located at the origin of the cluster. So you just have to use a function that retrieves the index of the atom located at the origin. Is that clear? Not too much? Okay, so this is just a number here. How to?
And sorry,
Yeah.
graphically, how can I check which is the index?
Okay, I will show you this.
Because okay, there is a list.
Okay, so this is the cluster. Okay, if you click on an atom, you see its coordinate. Okay, it's tagged, and this is number 4. Okay, and you use the hemispherical function, so you choose to locate the absorber at the bottom, so it is at 0, 0, 0, and this is number 5. Okay, so you could put cluster.absorber is equal to 5, but actually you don't know unless you you view the cluster, plot check the index of the atom by hand with your mouse, and if you are in a script process, for example, if you are in a loop and you change the emitter place on the cluster, it's not easy to do this. So you use the function to find which is the index of the atom at the origin. Right.
So then if you select this absorber atom by the coordinates, if these are real numbers, you have to be careful about the precision now.
Yeah, so there is a tolerance about so if you tell get atom index 0, 0, 0, this is the closest atom to 0, 0, 0. Okay, so it will give you the right number normally, unless this is really tight.
Sorry, if I don't have a graphical interface.
Yeah,
How can I print it? The X, Y, Z.
you can print the output of that function. If you print the output of that function, this is 5. This is 5. This is an integer. This is 5. Okay, just the number in the list of the absorber atom. So this is the first step to define a calculator. The second step. So first step is you create your cluster. Second step, you set the absorber. Third step, you create a calculator. So this methodology, creating a calculator, creating a cluster, creating an atoms object, creating a calculator, is the same for all ASE code, all code interfaced with ASE. Even electronic structure code is the same. Okay. So you define a calculator by using the MsSpec constructor object. Okay, so this is a class. This will construct a calculator to compute photoelectron diffraction signal. Okay, because I choose spectroscopy PED. Okay, so you are not required to put that keyword because for the moment there is only PED. Okay. But this is just to show you that after, if you want to make some Auger electron diffraction, it would be, for example, AED. If you want to make some lead, it will be LEED. Okay? There are other options, for example, the algorithm to use to compute. Like Didier said, there are several algorithms that we use to compute the result of photoelectron diffraction. So the total matrix inversion, which is the complete result, and some approximation with the series expansion or correlation expansion, etc. For the moment, only inversion and expansion algorithms are supported. And this is enough to compute for the moment a large majority of structure. So you created your calculator, and then you tell your calculator that you will use that cluster. Okay? So calc dot set atoms, I will use the cluster that I produced with the hemispherical cluster function. Okay? And finally, you can run the calculation. And the calculation you will have to run is a theta scan. So theta scan is a polar scan. Okay? So you will change. So here is your sample. Okay, so here is the normal. So you will change the polar angle of your sample, okay? So you will rotate like this. Theta scan. Phi scan like this, okay? Azimuthal scan. And you can make also a theta phi scan, which is stereographic projection. So you move theta and phi. This is better than making a loop over theta and phi, because you will not have the same number of points in the azimuth if you are close to the normal or very far from the normal, okay? So this line has some input parameters, because of course you know your emitter atom, but you don't know at which energy you will scan, okay? So to find the energy that you will be using, you have to specify which kind of level is excited on that atom. So I will choose the 2p level of copper. So I put 2p 3.5, but actually this is not spin orbit resolved for photoelectron diffraction for the moment. So it is 2p, okay? You can put 2p 1.5 or 2p 3.5 will be the same. And there are many other parameters, like the kinetic energy you want to scan, or the theta angle you will look for, and which phi angle you will be, okay? But by default, phi angle is 0, so you will look looking the polar scan in the 1, 0, 0 direction, okay? So you have to specify the level, and the kinetic energy, you are not required to put it. You can, of course, it is better, but if you don't know it, if you just want to run the calculation, it will be computed according a database inside the MsSpec. MsSpec will look for the 2p level of copper. It will look for your excitation energy source, and then compute roughly the kinetic energy that it would be for the photoelectron, okay? And yet you will have, as a result, as an output, you will have a data object which will contain all the results. This object is a special Python object, so this is not a simple list or a array or a dictionary. No, this is a bundle object, because you may have different scan inside the same object. But you can view it graphically. So you just have to write down data.view, and it will pop up a graphical window with the graph inside, and you can have all your parameters. You can export the data, save the data, print the data, etc. And in the end, last line, it is Calc Dot Shutdown. So this line is not mandatory, but during the run of MsSpec, actually, as Didier told you, MsSpec is a package, and actually behind the scene there are two programs. There are Fagen and there are Spec. So those two programs need input file and there are output file, and everything is written in a folder which by default is named Calc folder, okay? And in the end, if you want to remove it, you just have to write down Calc Dot Shutdown. It will remove that folder, temporary files. But if you want to keep it, to check or to use for future use or whatever you want, you can remove that line. It's not mandatory, okay? So here, I will show you how it works if you make the Python, this script you just saw. So if you run that script normally, I guess, yeah. So it will run, and you will have that window, okay, with the results. So here is the theta scan, the polar scan of the copper as a function of the polar angle, so of the function of theta, for phi equal to 0. And you can see that for the moment there is only one data set, but you can have other data set. The computed energy, the kinetic energy is more than 300 eV, but you can specify it to look for another kinetic energy. And in the view menu, you can show your data. So this is the theta angle, phi, energy. This is the cross section, and this is the direct signal. It means the signal that has not been scattered. Okay. It may be used sometimes to remove that part from the signal, but normally we use the total cross section signal. And in this view menu, you have also the cluster. So it is somehow the same kind of viewer than the AEC one. You can view your cluster, so you can move it with by holding the right mouse button and moving the mouse. You can translate it by with the left button. And if you hold down the control key and you use the mouse wheel, you will make transparency for all other atoms but the absorber one. It is easier for you to locate the absorber atom. Okay?
Could you show the Python script? It's not running.
Python script is here. So, yeah.
This is a 001 plane of the existing couples, right?
This is the 001, yeah.
There's a four-fold symmetry.
Four-fold symmetry, yeah.
And especially mirror symmetry along this line we are scanning. But the output does not show its mirror symmetry.
You mean there is no mirror symmetry between here and here? Yeah. Why so?
That's my question.
Because of the geometry of the analyzer. So the source is not the X-ray is not like this. It is like this. So this is how this is why there is an interaction, and this is yeah. Those parameters we will go into details after. Yeah. You can specify. Of course, it's an important parameter. And this is the occasion for me, thank you again, Peter, for me to tell that it's important when you do calculation in photoelectron diffraction using the multiple scattering approach, give all the parameters in the paper. Otherwise, it's impossible to guess what is the geometry of your analyzer. Really, it's difficult. So if you want me to continue to write tutorials, so, okay.
Can we change here the kinetic energy?
Sorry?
Can we change here?
Yeah, no, not in the graphical interface, but in the script you can add the keyword. So in the, so here, sorry. So here in the calculation function here, get theta scan, so you have the level keyword. Then you can put comma, kinetic underscore energy equal to, and you put your value in electron volts.
And if there is blank, then what kind of kinetic energy is it?
That's what I was saying a few minutes ago. So it is computed according to the level that you specified here, okay, the electronic level, and the energy of your source. And the default energy of your photon source is the mgKL, okay, lab source, 1253 eV, okay, plus minus 4 or 5 eV to take into account the work function, roughly, okay. So if we go back, sorry. Okay. If you go back to the viewer, you can use file save as to save your data as HDF5 format. So it's nice to retrieve your data, but okay, it's not really easy to use for a format, but it can store a lot of data and can store everything here. But if you want, you can also export this data. So you just have to click on File Export. You create a folder, for example, results. And you go inside that folder, you open, and it will export the data. And if you go to a file viewer, so where am I? MsSpec. Okay. So in the results folder, you will have one folder per dataset. So here there is only one dataset, so the first one. And in each folder, you will retrieve a picture of what you are seeing on the screen. And you will retrieve a text file with every parameters of the calculation in the header and every columns, the data that you had on the interface. Okay, so it's easier for you if you want to proceed the data to another level. Okay. What to say more? Okay. So here it is for the interface, for the basic. Yeah. So if you didn't save it as a HDF5 format, it will complain that it is unsaved. And here the calculation is only 30 seconds, but sometimes the calculation, well, more often the calculation is around several days. So it's better to warn you. And of course, you can save the data directly from the script. You just have to write down data.save, the file name, okay, instead of data.view. Okay, so you will save your data in a file. So yes, I want to quit.
I have a question.
Yeah.
It seems to not work in an interactive Python.
In interactive Python. Okay. Yes. In interactive Python, it's not working. Yes, it's normal.
Oh,
You have to write down a script. Yeah.
Oh.
It's normal because it creates some temporary files. So that's why I'm guessing that it's interfering. But in interactive Python, you can practice ASE, for example, to create your cluster. And then once you're happy with this, you can migrate those lines into a script. Okay? But the better approach, one that works every time, is build your script and use the view function. Or instead of using the view function of ASE, because you have to import it, you can use the edit function. So the problem with the view function in ASE is that if you view cluster, if you add this line in your script, it will pop up the graphical interface and proceed to the line after. So it won't break your it won't wait for any instruction. So it is a different thread. Okay. If you want to stop the execution of your script, see your cluster and exit, you can use the edit function. So this is cluster dot edit, and it will pop up the same window. And in that case, you can even use the tools in the graphical interface of ASE, for example, to remove an atom. It will be saved, meaning that once you close the window, the line after, there will be an atom less on your cluster. So it may be sometime handy for some purposes. Okay? So here is for the copper. This is really the basic example. I will move the script. Was everyone able to pop up the result, the graphical result? Yes? Okay. Fine. Sorry. So here, to answer to Peter, here are a list of parameters that may be used. So this is not all the parameters used for making a calculation. This is the most used parameter for making a calculation. So they are sorted in different categories. Okay, so the first category concerns the potential, the muffin tin parameters for creating the potential. So there is the ionicity keyword. You may specify some redistribution of the electrons of your atom. So if you look, for example, for in MgO, you can remove some electron from Mg and add some electron to oxygen or whatever. But in the end, as we are looking at usually quite high energy, there is not much difference in the results. And one interesting parameter is the interstitial potential. So this is the value that for the potential in between scatterers. Okay, and it is really important because in photoelectron diffraction, this creates a refraction angle when you escape from the surface. So it may shift the peaks that you detect. So usually this interstitial potential is around 5 to 15 eV. Okay, and it's important to put it if you want to match experimental data. So the unit is in electron volt. Yes, units are in electron volts for energy and in angstrom for space unit. Okay. Then you go to the section for T-matrix parameters. So for T-matrix parameters, they are the exchange correlation function. So for computing the T-matrix, we need the Coulombic part of the potential, and we add the exchange and correlation part to the potential. And this exchange and correlation may be the Edwin-Lundquist function, X alpha, Dirac-Ara. There are many different possibilities, but you have to keep in mind that there is a real exchange and correlation function, or the complex counterpart of this function. If you use a complex exchange and correlation function, the the mean free path, the attenuation for the electron, will be computed according to this imaginary part. Otherwise, if you use the real exchange and correlation function, you have to specify the mean free path of the electron. Okay, so this is usually done in single scattering calculation. They put so this is single scattering calculation, and they use real exchange and correlation function, and they adjust the mean free path of the electron to fit the data. So usually it's better to use Edwin-Lundquist complex. So there is nothing to put more in your calculation. Lmax mode. So this is an important parameter. So this will control the number of TL that will be used for the calculation. So Didier told you that, for example, at low energy, it's rather small, some few TL, so 3, 4, 8 maybe. But usually, due to the experimental setup in lab source, photoelectrons are in the 500 to more than 1,000 EV range. And here we need more than 10, 15, 20, 25. So honestly, above 25, it is really, really difficult to make a calculation. It may be very long, and it may be somehow buggy because of precision due to an exponential.
Yeah, in addition, there is the problem of the solving of the Schrödinger equation, and the maximum we have tested so far is about 35. So we don't know yet. We don't know anything concerning stability of the Numerov method. Higher for angular momenta higher than 30, let's say 35.
So you can choose to set this parameter to the max kinetic energy keyword. So it will compute the number of Lmax according to your kinetic energy. This true KE keyword will compute the Lmax according to the max kinetic energy and according to the type of atom used, because you will need more TL for strontium atom than for sodium, for example. And also you can impose your choice of the number of Lmax. And this will be used with the Lmax T keyword. So if you choose imposed in Lmax T, you write down the number of TL that you want. So it may be nice if you are willing to debug your script. You can run a calculation with Lmax mode imposed and Lmax T 3, for example. It will be very fast, and you will see if your whole Python script is working. And then you will do your calculation by removing by setting a correct value for the Lmax. Okay. Again, to play with the TL, there is a threshold, TL threshold keyword, which is now for the moment the default value is 1 to -6. So it is a filter. So every TL that is below this value is removed from the list. It is not used because it is considered to be too low. Okay. You can choose another value for this one, and you can also set a number or a maximum number of TL value for each kind of species. For example, you can tell In MgO, I want 20 TL from Mg and 15 for O at maximum, meaning that if you are looking at low energy, it will not be used, but if you are working at a higher energy and that you would have to use 25, for example, for Mg, it will stick to 20. Okay? So these are the keywords for controlling, though this is more related to Fagen, actually, for controlling the computation of the phase shift. Now comes the keywords for controlling the parameters for controlling the actual multiple scattering calculation. So there are three categories. So the source parameter, what are your photons, the detector parameters, the geometry, and the calculation parameters. So for the source parameters, you control the energy. So here is the standard energy for the MgKLL source in laboratory. You may change it to whatever you want. This is just a number. The theta and phi angle, so this is the position of your light according to the origin. Okay. So this is the geometry. I'm not sure this is our geometry, but somehow it is normally most of the spectrometer share almost the same geometry. Sometimes it's more or less. And then no, sorry, copy-paste error. There is no TL threshold. Of course, it's on the previous parameters, so this line doesn't exist. Detector parameters, so you have the angular, again, copy-paste error, sorry. Angular acceptance, so usually this is the angular of your acceptance of your spectrometer. This is probably a few degrees, okay, not 100. The angular acceptance. And the average sampling, so usually in the photoelectron diffraction calculation, you calculate one direction, okay, at a certain angle. If you want to be more representative of your experiment, you can average several directions close to the direction that you are looking for, okay? So this is the average sampling parameter. If you set it too low, I guess, so to none, there is no averaging. This is the direction you are looking for. Low is, I don't know, 5. Then medium, I don't remember.
This is simple. It's just a grid, which is a. So we assume that your analyzer has got a circular acceptance. So here is the direction of your electron. This is the acceptance of your analyzer. So if you set too low, you've got, in addition to this, you sum over these points, these directions. If you set then to the next one, you divide everything by 2, and you include all the new points which are inside the circle.
So you have a none, low, medium, and high. Okay? And for the calculation parameters, so there are many parameters for the calculation, but what we will be using for today, and most of the time, you will have to control the scattering order, which is only relevant if you use the series expansion algorithm. So it means how many scattering events you will consider for a photoelectron. So by default, this is 3. It is limited to 10, but honestly, above 6, it begins to be very, very long for a calculation. The rare Albers cutoff parameter, so the default is 2, I guess, and this is this control the amount of sphericity that is included in the description of your wave function. So the more is better. 1 is too low, but it is faster. And path filtering. So in series expansion, when you compute the photoelectron signal, you have to take into account all paths of the electrons. So you may have, for example, something like this. So this path is taken into account. This path is taken into account. But there is also, for example, this path. The electron will go there, will go back, and will go there, for example. Okay? So this path, due to the backscattering, 2 times backscattered, it will be very low because the probability to be backscattered is low at higher energy. So this path is not supposed to be very important in the total. So you can avoid computing it, and you will restrict your path to a given cone. Okay, so it means that you can filter out. So if I go back here, if you look at that direction, for example, and you know that the scattering factor is like the one I represented in the first slide of the presentation, you will be selecting only paths that are in this cone. Okay? You do not take into account paths that start like this, because the probability of this is very low. Okay? So this path filtering allows you to remove a lot of paths that are not with very low intensity in the total. Okay? And it will speed up the calculation a lot, and a lot if the cluster is big. The bigger it is, you will get a lot of the speed will be very higher. Okay, and then the final keyword is the vibrational damping. So this will model how the temperature will affect your results. So when you vibrate your atoms, they appear bigger than they are for the photoelectron, and this vibration, of course, will damp the signal. So the modulation that you will observe will be lower, or some interferences may also disappear. And this is modeled with this keyword. So there are two ways of modeling it. Either you use the Debye-Waller approach, or you can use the averaging of the TL, which is a more correct approach. So an averaging over the TL is done. But anyway, whether you are using Debye-Waller to describe this or averaging over the TL, you have to provide the mean square displacement of these atoms, so you can specify them by hand. Okay, you tell these atoms the mean square displacement is 0.04, for example, square angstrom, or you can use the Debye model. You set the Debye temperature, and it will be computed automatically. So we will be doing this in a tutorial this afternoon. Okay, and finally, sorry, it was not okay. It's better like this. And finally, I show you in the last script that we used, for example, how to change a parameter. Here, for example, I am interested in a source parameter's energy. So this is calc dot source parameters dot energy, and I choose to change from mg k alpha, which is the default, to al k alpha. Okay, and you can put also directly a number. If you want source energy is 200 eV, you put 200. Okay. And this is the same for all parameters. It's just for the return of this. This is just a key equal value pair. Okay. So that was for the copper example. I don't know when is the break. It is 12:30 or.
Yeah, we have to be at the restroom for 12:30. So
okay.
Finish at 25 past.
Okay, so we can start the tutorial on the nickel. So I will share. I shared the. Okay, do you have any question on this? It's clear, yeah. Yeah.
It's the lead type of approach where you replace the TL by an average TL. It's what they did. What they do in lead, in the old lead platform, in the lead theory.
So it's different from what we do for vibration?
Yes.
Yeah, it's the starting point, so you just average over the T matrix. I think you will displacement you have maybe.
Yeah, I
don't do CPA, but it's like
Average T matrix.
I think
Likewise, you have to.
So normally you do have the nickel chain example. No, it's empty. Okay. So it disappeared again. Right? Can you see it? Can you have it? You can download on your home folder. So here you have the PDF of what I am projecting, and you have also a paper. So from now, all the tutorials are based on a paper. So you have either experimental results from the literature, or calculation from the literature, or both. And we try to reproduce what is in the paper, okay? Somehow, not all what is in the paper, and close to the paper, I would say. So this is not recent papers. This is papers useful for comprehension and for tutorials. So we'll talk about the defocusing effect in photoelectron diffraction. So for this, we will look at an example, purely calculation example. So this is the nickel atomic chain. So we will have a chain of nickel atom, and we will have more and more atoms in the chain, and we will look for the signal. So here is the result if we are using the matrix inversion, so the true solution, the exact solution, I would say, for the nickel chain. So here I have my emitter atoms and the first scatterers, and here is my detector, and I'm looking at the signal, okay, as a function of the polar angle. So it means that I have a strong peak at 0 in the forward direction due to the scattering factor, of course. And so in matrix inversion, what is the result? So if you add some more atom, the peak, the forward peak, is always focused, but the signal starts to decrease. And if you have more and more atoms, you will decrease the signal and end up with no signal atom. So this is the defocusing effect. So you have the forward focusing effect, which will focus your electron along dense atomic direction. So this is a dense atomic direction, but at some point you will defocus it. And classically, it may be understood as if your electron is over-focused. So it is so focused that at some point it starts to diverge. Okay? So it is only this result can only be calculated with multiple scattering approach. If you use the single scattering approach, you will never observe this decrease of the intensity of the forward peak. And the problem is that you have to use you have to compute the cross section. So to compute the cross section in MsSpec, you will it's a matter of computing the scattering path operator. This scattering path operator, as Didier wrote, it's not there anymore, wrote down here, it is this inverse matrix. So the matrix inversion algorithm will compute the full solution. It is exact, but the problem is the storage and the time to invert this matrix. So as an example, this is just an example of a calculation. If you want to compute the signal, the PED signal for 1,000 of atoms at 1,000 eV, which is what you could do in reality, I mean, to fit an experiment, it would take too long and too much memory, even of a big node. So for this, we use the Rao-Albert series expansion method, which is this approximation where you set the scattering order, okay? And if you take scattering order equal to 1, you will have something similar to single scattering experiment, single scattering calculation. And if you increase the scattering order, you will be close to the matrix inversion result. And this was studied so years ago, 1998, by the group of Van Nove. And here is the result. So they look at an atomic chain. Here are 2 atoms, so 1 emitter and 1 scatterer. And here a chain of 5 atoms. And here is the result in single scattering. So the peak is the same if you have 1 atom or 5 atoms. And if you use multiple scattering, you have the peak, the strong peak with 1 atom, and it is disappeared with the total chain. So we will try to reproduce this with MsSpec calculation. Okay? So here it is. So as it is only your second script, I wrote most everything, but I leave some holes in the code source, in the source code. So you will have to complete this to produce the results. So please.
So he didn't say it, but this is an IQ test.
So you here. So I just walk through the script. This is easy. Actually, this is really easy. So as previously, so you have to write down those 2 lines, okay? Then you import the MsSpec calculator, and this time, as we are constructing a object which is not, physical, it's just a list of atoms. So you will import the most basic object of ASE, which are the atoms object and the atom object. So atoms is a list of atoms. This is only this in ASE. And of course, you need NumPy. You know NumPy, yeah, of course. Yeah. So here is the body of the script. So I choose to use some global variables. So which kind of chain I am looking for. So for example, nickel, but you could choose anything else. So what is the distance between 2 nickel atoms in 101 direction? Because I will look that direction. And then here is how you can create this object in ASE. So I define a chain. So this is my variable, which is an empty list of atoms. So there is nothing inside. And then I add an atom at position 0, 0, 1, 1A, and an atom at position 0, 0, something else. And then to fit the result in the paper, I have to rotate my chain, because here I put my atoms along the z-axis. So I have to rotate my chain 45 degrees along the azimuth equal to 0. Okay? So you will find it by reading the documentation, because as I said, if you want to be an ASE expert, read the doc. And finally, you have to define the absorber atom. Which one is the absorber in this chain? The absorber atom, you have to find the index of this one, okay? And the second part of the script, so the second part of the script is you have to create a calculator to compute this. So of course, you won't use matrix inversion, because here we are willing to check the difference between single scattering and multiple scattering approach. Of course, you set the atom, so I wrote this line because this is the simplest one. And then you tweak the parameters. So as I told you, to change a parameter, you do like this, calc dot the category of your parameter and the keyword. And for the first calculation, it is 1, just single scattering. Then you compute the theta scan, choose your level, the theta angle. And here, that you could not guess, here is how to append data. So in the previous page, I define the variable which is none, which is all data. This is a variable that will be holding all the results. So this is none for the moment. After the first calculation, this is none. After the first calculation, it will be overwritten, and it will contain the result for the first calculation. If you add a second line and you use all data again in the data keyword, it will append the data to that data and overwrite it. Okay? So this is how you can add more data set in the same object. Okay? So this is this line. Then all data.view, as previously in the copper, and shut down if you want to remove all temporary file. Okay? So I let you find the solution, and we'll go for this perhaps this afternoon, and look for other tutorials. Yeah?
I have many questions, I'm sorry. Now, to do such a thing, if you don't master well this Python AC, so it's a bit complicated. Don't you have a method to import a cluster from a common format like
Yeah.
X, Y, Z?
Yeah. So in ASC there is in ASC.io package module, there is a read function, and you use the read function, and in the argument you put your file name, and it will if your file name is PDB, XYZ, whatever, it will import it, and you will retrieve an atoms object in one line.
This is totally compatible with your...
Totally compatible. Yeah. Okay, so let's do it. Filling the holes.